Hello and welcome to lecture 32, the substitution rule. Okay, so what have we learned? We've learned from the fundamental theorem of calculus that if we have some definite integral, all we need to do to calculate this is to find any antiderivative of little f and apply the fundamental theorem. Okay, so the hard work of looking for solutions of definite integrals now just becomes the search for antiderivatives. So a lot of the remainder of this course and a big chunk of calculus 2 will now be techniques to find antiderivatives. And what we're learning now is the very first such technique, the substitution rule. So, things to say about this. Firstly, doing these things, finding these antiderivatives, doing this integration is somewhat of an art as well as a science. So, even a craft. I will present some basic things in this section about how to do this method, but I can't give you simply an algorithm where you do step 1 up to step 5. Some of this is where you're going to be looking at something, trying to make the right choice of the substitution U, which we'll see in a second, seeing if it works, giving it a go. Maybe it's the wrong choice, trying another choice, just building up your intuition as to what the choice is to make. And the only way to build an intuition is to practice this and to do lots of examples. But you do have to do that because this section will be used over and over again for the remainder of the course, because this is one of the basic tools for integrating. So we're going to teach you a whole bunch of different tools to integrate functions. By that I mean to find antiderivatives, lots of times, or to calculate definite integrals in some cases. And they're almost the same thing thanks to the fundamental theorem of calculus, but we'll see they're not necessarily exactly the same thing. More on that later. So we're going to teach you a whole bunch of tools to do integration, and you're going to have your toolbox of integration tools. And then you're going to be faced with some integral, and you're going to have to pick the right tool. So you're going to be using this in future problems, even outside of this section. So if you just think, okay, this stuff is too tricky, I'm just taking a 0 on this, that it's going to be more than a 0. It's going to be a 0 that continues in many future sections. So the way to get good at integration is to have the whole toolbox. And if you don't have the whole toolbox, expect to have big problems. So you need to solidify, get good at all of these techniques, but it is mostly the practice of an algorithm. And it's not fully an algorithm, it's an algorithm with a certain kind of good choice, a certain creative choice sometimes. But mostly it's following an algorithm. This isn't a particularly hard section. Conceptually, this really isn't a hard section. Okay, so let's launch into it. So I'm going to do the first example, and I'm going to show you the method, and it'll seem somewhat magical. I'll do things that make no sense, but it'll give me the right answer. And then we'll talk a little bit about why we got away with it, why this actually worked. So this is our first example. Okay, so right now we don't have any of the stuff that can help us. We can't just easily guess this, or at least most of you can't. So we can't just, most of the stuff we know about finding antiderivatives is just working backwards from differentiation, right? So we can find the antiderivative of a power law because we know how to differentiate. Start again. We can find the antiderivative of x to a power because we know how to differentiate x to a power, right? Nothing so obvious here. So this is what we do. We're looking for some u that we can define to be some part of this, where if we let that u be that part and we try and replace everything else, we can replace this entire integral in terms of u. And that new integral in terms of u will be an easier thing to study. Okay. So in this case, the u sub will be the 1 plus x squared. And it's often the case that you're going to take the u sub to be whatever's inside the square root. So let's take u to be 1 plus x squared. If we differentiate this, we get this. Okay, now here is the part that makes no sense, but nevertheless still gives us the right answer. We are going to pretend that du over dx is actually one number divided by another number, which we can just multiply through by. So we're going to multiply through by dx. And we're going to write du equals 2x dx. This makes no sense. This is absolutely not one number divided by another number. This is utter nonsense. This is just nonsense. And it's important to me that you know the difference between things I write that are valid and things that are nonsense. This is nonsense. This is pure nonsense. However, it's nonsense that we can get away with for reasons I'm going to explain shortly. So let's do this nonsense. And then we have the u is 2x dx. We can look at this thing and we see that there is this 2x dx here. Let's rewrite this guy. Yeah. And then what? We have this right here. Right here is something we could replace by du. And this thing here, this square root of 1 plus x squared, this thing right here, this is just going to be square root of u because of the definition of u right here. So we can turn this entire integral into an integral just in terms of u. So this is the integral of the square root of u du. Yeah? Cool. And then this is an easy integral to integrate, right? This is just the power of u. This is u to a half. We know that in order to differentiate something and get it to be u to the half, the power has to be 3 over 2. If we differentiate u to the 3 over 2, we have 3 over 2, u to the half with the wrong constant in front. So we're going to divide by 3 over 2, which is like multiplying by 2 over 3. So then we're going to have 2 over 3 u to the 3 over 2 plus constant c. Yeah? And this is not done because this is in terms of u. We're going to turn it back in terms of x. Cool. And now we can check it. Now if we differentiate this by the chain rule, oops. And I drop the square right here. Constant c just drops out. If we differentiate this by the chain rule, the outer function is x to the 3 over 2. So this is going to cancel this 2 over 3 over here. So it's going to be 1 plus x squared. Take this down by a power, a half. And then we differentiate the inner function, we have 2x, right? And that's exactly what we're looking for. So this thing right here is indeed the antiderivative of this expression. Yeah? So it gives us the right answer, this crazy procedure here where we treat du dx as if they're one number divided by another number. This is something that works out. Okay, another thing to note is that in all of this stuff of finding antiderivatives, I mean people like me who are easily making small algebraic mistakes, even in things we think we understand well, we tend to suffer in multiple choice exams because it's very easy to drop a sign or whatever for a 2 to become a 3 because you're writing fast and you don't look carefully enough what you wrote the line above. And that means losing a full 8 points, even in things that were almost correct. So it's really bad for people who make small, careless mistakes to do multiple choice exams. And that's something I had to work a lot at to overcome. And the great thing about this is that you don't have to suffer so much, because whenever you find the antiderivative, you can, just like here, just differentiate it to check that it's the thing you expect it to be, the thing you want it to be. And it's almost impossible that you will get the wrong antiderivative and then somehow wrongly differentiate to get back to the thing you're expecting to find. These are completely different procedures. If you make 2 errors that somehow cancel each other out from these completely different procedures, it's like 1 in a million. So if you find your answer differentiated in and is what you want it to be, you can be happy that you've actually nailed this question. It's 8 points in the bank. No thing to worry about. So I strongly recommend all of you to not leave the exam before you've done this kind of thing. Anytime you have an antiderivative, you can check for certain that it is the right thing by differentiating it takes whatever, 30 seconds, do that. If you're really ashamed to work hard, to spend all those hours doing homeworks and coming to classes, watching these videos, and then lose 8 points on a 100-point exam because you did something really, really ridiculous that you would have found in 30 seconds if you double-checked. So please do that. Please double-check with this. Cool. So we have the answer. It worked out. It's not clear why this worked out, but let's try and figure it out a little bit. So recall the chain rule. Suppose we differentiate capital F of u of x. What is this? This is f prime u of x times u prime of x, right? So, if capital F is the antiderivative of little f, i.e. capital F prime equals little f, then look at this. If we consider this, since little f is just capital F prime, this is just this thing. And by the chain rule, that thing is just the derivative of f composed with u. And what's this? This is just f of u of x plus constant c. Yeah? Cool. So, why is this relevant? Well, if we look at this example over here, let's call this example 1. So in example 1, maybe I'll put it down here. If we try and get this thing into this format here, where we can make sense of it, then we see that the u is indeed well chosen as 1 plus x squared. And we see that the f is well chosen as the square root of x. So then this integral, let me just write the entire thing. So 2x square root of 1 plus x squared dx with this choice of u and f is now the integral of f of u of x, u prime of x, dx, right? And then this is what we just learned, that this guy is just the antiderivative of little f applied to u plus constant c. And the antiderivative of little f is x to the 3 over 2, 2 over 3. So this is indeed 2 over 3. Now we're going to put what u is. U is 1 plus x squared. The 3 over 2 plus constant c. And we get back exactly what we got before. This is the same as this. Well, better to say this is the same as this, because I didn't bother to include the c in that differentiation. So what we did here is actually the same as what we did here, except in this procedure here, we had to look at this and we had to carefully choose the inner function, which was u, and the outer function. Yeah? But we found those choices, and then this guy, or this stuff here, is just doing the reverse of the chain rule, right? The chain rule does this for us, right? It allows us to differentiate this composed function. This is from the output of the chain rule, and we go backwards with the integral, and we get back to the composed function. So this U-substitution is actually just doing the chain rule in reverse, yeah? Which also makes sense from the fact that we checked it. We checked that our answer was correct by applying the chain rule here. So the moral is that this stuff here is actually just this stuff. It's just doing the chain rule in reverse. And this weird stuff we're doing here is basically a notational shortcut, which allows us to just focus on finding the u. So we don't have to look and try and find the f in this stuff, which is what we did here. We can just find the u by this notational shortcut. Let me emphasize, this is not a proof. I haven't proven this at all, and it is possible to prove it, and that's hopefully what you'll see as you learn more mathematics. And it's not even difficult to prove it, and as always, the proof is a picture, or actually a couple of pictures. This is just an example of getting the same result on this. This is getting the same result on this specific example from doing the chain rule in reverse. And it's just to motivate you to believe that what is happening here isn't just crazy magic. It isn't some weird, crazy stuff. It is just doing the chain rule in reverse. It's not a proof. I'm not proving things in this course. I'm just drawing pictures, and this is absolutely not a proof because all I did was check it in a different way for a single example. But hopefully it's enough to make you feel like this is reasonable. This is not some very difficult, deep, complicated thing that I have to be scared of. It is nothing particularly difficult. It is just essentially a notational shortcut for this. Cool. All right. So we have this tool, and we have to practice it. And let's do some more examples. Let's call this example 2. Let's do this. Okay, so the game for us, the thing we specifically have to learn is to find the u. And in the first few examples, the choice will be relatively easy. So if we look at this, we are hoping to find a u such that when we write the u dx and then break it up to write du equals something times dx, that something times dx is the stuff I can pick up on the outside. And that's what I see here. So this is the stuff on the outside. So if I let u be x to the 4 plus 2, then du by dx equals 4x to the 3, And then we do this breaking up of the du stuff. So we're going to have du equal 4x to the 3 dx, divide through by 4. Then we're going to have that du over 4 is equal to x to the 3 dx, and I pick up exactly this stuff here. This stuff, I've picked it up. So then, call this integral star. In star, I can do this. I'm going to replace this x to the power 3 dx just with du over 4, and then this thing, I'm going to replace this x to the 4 plus 2 with u. Of cosine of u du over 4. And then we can pull out this 1 over 4, and then we integrate this, and then what's the antiderivative of cosine? It is just sine, right? Plus constant c, and then let's put this stuff in. Let's put this stuff in. So we're not finished because we need to put things back in terms of x, and we have substitution x to the 4 plus 2 plus constant c. And we can do a quick mental check. If we differentiate this, the outer function is sine. We differentiate, we get cosine composed with the inner function x to the 4 plus 2. And we differentiate the inner function. We're going to have 4x to the 3. The 4 will cancel this 1 over 4. We're going to get cosine 4x. We have cosine x to the 4 plus 2. And then x to the power 3. And that is exactly what this is. This is correct. All right, cool. So I'm going to raise the board, and we're going to practice this some more. Okay, let's do this example. If we have this thing, then this guy here is hopefully somewhat straightforward. Again, there's a decent rule of thumb that one of the first things to try is to just put everything inside the square root as the u. Again, I emphasize try. It's not necessarily going to be the correct thing. In this subject, in this method, you are going to have to accept to try things, try and get them to work out, and then if they don't, then try a different choice of U-sub. But this is always a natural and a good choice to make. And in this case, I'm pretty sure it is going to work because this is what I call a linear substitution, because this is a linear function here, this 2x plus 1. And linear substitutions are incredibly cheap because the du is almost the same as the dx, it's just multiplied by a constant, right? So du by dx is just equal to 2. So this dx is almost the same as du. It is just du over 2. So if you look at some expression where you have a linear thing and then acted on by other things, and you can see that you just replaced the linear thing by a u, and then it's something you can handle, then just do it, because the dx is almost the same thing. It's just changed by a constant. Huh? So then this integral here is the integral of the square root of u of u over 2. And then what do we do with that? Well, then we're kind of in good shape, right? We know the antiderivative of u, it is 3 over 2 times 2 over 3, like this. So then, oops, plus constant c. And then this is just 1 over 3, this stuff, 2x plus 1, to the 3 over 2, ouch, plus constant c, and we're good. We're completely good. Yeah? All right, let's do another one. Okay, let's do this one. Example. So, let's do this. Okay. All right, so a really good thing for you to do if you're watching this on video, haven't been in my in-person class, is to try this one yourself. So just pause the video, give this one a go, try and find the u, try and turn the entire integral into u, try and integrate that integral in terms of u, and then turn it back into x. So give this a go, give it a good shot. This one isn't so easy. You're not going to have this fallout view just in a couple of steps. You're going to have to fight a little bit for this to work. But if you try it long enough, you will get this. You will get this if you've understood what we've done so far. And the best way to actually learn this is to give it a go before you watch what I do. So pause the video, give this one a shot, give it a good go, try for at least 10-15 minutes before you give up, and then press play and see how I do it. Okay, solution. So as I said, a rule of thumb is to take the stuff inside the square root as the u. That often works, so let's give that a go. Sorry, start again. Yeah, I did say it right. The stuff inside the square root as the u, so like this. And if we do that, then what do we get? We get that the u by dx is equal to 2x, right? So this implies that the u equals 2x dx, and let's divide by 2. So this implies that du over 2 equals x dx. Okay, so not looking necessarily too good for us because what? Well, because we have not got just x dx, we have x to the 5 dx. Yeah? If this was just square root of 1 plus x squared x dx, then we'd be fine. We could turn it into u straight away. But we don't have that. Yeah? So, if you look at this, you have two choices. You either keep struggling with this, trying to make this substitution work, or you try a different substitution. And any of these things, there's only finitely many substitutions you can try, so you're ultimately going to find it if you try long enough. But there's also the balance of, do you keep trying with the U, or do you give up and try another one? In this case, we're not going to give up, because we see that, let me get some colors, we see that this part's okay. We can turn this stuff in terms of stuff to do with U because of this. That part's okay. What we have a difficulty with is the rest of it, right? But let's rewrite this integral. Let's call this thing star. So let's just do a little bit of algebra, and then this thing becomes integral of square root of 1 plus x squared. Let's write x to the power 4 x dx. Yeah? Cool. All right, now, then we see that this x dx stuff, we do recover. We do recover this x dx stuff. This is the x dx. This is the x dx. Yeah. And then what? Well, then we are in good shape, except for this power of 4, because again, this thing can be termed in terms of U. So this x to the power 4 is the thing that gives us a problem. Yeah? But if you look for a while at this sub right here, then what you will notice is that U minus 1 equals x squared, right? So in particular, if you square both sides, you're going to get that U minus 1 squared equals x to the 4. And then this part here that we were having a problem with, we can now handle because we can replace it with this thing. Yeah? I hope the colors differentiate enough for you to see that as I want you to. Cool. So then star becomes the integral of the square root of U. This x to the 4 is now this U minus 1 squared, and then this x dx is now just du over 2. I'm going to put this over 2 over here straight away. And now we're happy because this thing, even though it might look not that much better, look at it a bit longer, you see that we can just expand out this square, and then we get the following. Square root of U, U squared minus 2U plus 1 du, and then multiply through by this stuff. So 1 over 2 integral U to the 5 over 2 minus 2U to the 3 over 2 plus square root of U du. Yeah? And then what's this? This is 1 over 2. And all of these things are just powers in U, right? So we can find the antiderivative of each one of them. Huh? So we're going to have U to the 7 over 2, 2 over 7. Yeah? Right here we're going to have 2, and then this will be U to the 5 over 2 times 2 over 5. Yeah? And then here will be U to the 3 over 2 times 2 over 3 plus constant C. And then we just put this stuff through. And then what do we have? This is this. Here we go. Here is our, where is our U? There we go. Our U is over there. So now we're going to put everything back in terms of U. So 1 plus x squared to the 7 over 2 over 7 minus 2 over 5, 1 plus x squared to the 5 over 2, and this now becomes a third because we're dividing by 2, 1 plus x squared to the 3 over 2 plus constant C. Yeah? And that's it. That's our answer. Yeah. So we had to just persist a bit longer to fight to get this in terms of U. Yeah. It wasn't just in one step. We had to figure out what to do with this. Yeah? And then once we did this and got something in terms of U, we had to further think and realize that we can expand this out into just having a bunch of sums or subtractions of powers of U, like this. And then powers of U, for sure, we can find the antiderivative. So it can get a little bit trickier, but all the individual steps themselves are not particularly hard. And you will all be able to find this. Yeah. So hopefully you did pause, give this a go before watching me do this. But I guarantee you would all have found this if you'd tried long enough, because there's only finitely many things to try, right? So if there was just, if you're in jail for a day and the only way to get released was to solve this problem, you would solve the problem, right? You would eventually come up with this, right? And once you see it, you see it's actually not so difficult. And the way you're going to build up your intuition of what to do these things, or what to do with these problems, is to go through that, is to look at something which initially might be hard for you, that'll take you 10, 15 minutes, and to not give up, to just keep going, keep trying. There isn't any shortcut here. There isn't any magic solution. There isn't any YouTube video I can link or book I could give you or anything that's going to subtract the need to just persist to build up your intuition for these things. And in fact, persistence and accepting some stress in this process, maybe stress is too hard a word, accepting some difficulty is part of learning math, like it or not. All right, so that is that example. Let's now talk about using Usub for definite integrals. So we can certainly do this stuff to calculate definite integrals, because once we have the antiderivative, then we can find the definite integral. So if our problem, for example, was to calculate this from whatever 5 to 12, yeah, then it would just be ultimately plugging in 12 into this, subtract 5 into this, yeah. So we can use this, but there's a way to get the answer faster, which is to evaluate the definite integral directly in U, instead of going all the way and finding the antiderivative in terms of x. So at this point, we have the antiderivative in terms of U, and then we turn it back into x. We can avoid that step if we evaluate it in U. And this is how it works. Let me first give you the general principle. Okay, so general principle is as I explained before, that if f is the antiderivative of little f, then capital F prime equals little f. That's the definition of antiderivative. Yeah. So then if we have an expression like this, if we have a definite integral of this form, a to b f of u of x, u prime of x, dx, right? Then that is the same, putting in that capital F prime is this thing, that's the same as a to b of capital F prime, u of x, u prime of x, dx. I'm making these steps as small as possible, so this seems kind of transparent. And then we know that this, by the chain rule, is just this, right? This is just the derivative d by dx of f of u of x dx. Yeah? So we have the antiderivative, right? Start again. No, not start again. We have that this guy is the derivative of this guy, and then this is just going to be applied to the fundamental theorem of calculus, net change theorem. This is the version of the fundamental theorem where we apply it directly to the derivative, which is the net change. Let me put that up here somewhere. I talked about it just in the last video, but just to make it totally transparent. So the net change formulation of the fundamental theorem is when we do this, and it's just equal to g of b minus g of a, right? That's net change, huh? So our g in this guy is just f composed with u, so just by this is just capital F of u of b minus capital F of U of A. Yeah. But that is also the same as what we get when we just integrate from U of A to U of B, little f, with respect to U. Because capital F is the antiderivative of little f. Yeah? So this problem right here gets turned into this problem right here. Let's underline it. This thing becomes this thing. And let's show you that in action. Let's do this example. Zero to 4, 2 x plus 1 dx. Then, okay, so we know what to do. This is something we've done before, this particular problem. We know to take u to be this, 2x plus 1, and then the du is just 2 dx. I'm doing this just in one step. We've done it several times before, and therefore the dx is equal to du over 2. Yeah. So in this example here, we turn this thing into an integral in u. So first let's write it as an integral in u. So we're going to have square root of u, and then this dx is just now going to be du over 2. So let's just put this over 2 du right here. Yeah. But now we're going to have to change the limits from being limits in terms of x to limits in terms of u. And we look at this thing right here. U is defined by this. So then when x is equal to 0, this just becomes 1. And when x is equal to 4, this becomes 9. Yeah? And this is just doing this right here. Yeah? This is just doing this right here, because in this case, the f is the square root, yeah? And the u prime is the 2, so I could just multiply I can multiply this through by 2, and then I'll have that this is 2 dx like this. Yeah, it's exactly the same thing if I do this. Let me write that better. Yeah. So the f again is the square root. The u is this thing, right? Just like this. So this thing here is f applied to u. Yeah. And I want to put f as the square root somewhere just to highlight it. F is the square root. Yeah. And u prime is 2. And then this thing is equal to this thing. When we change the limits and write the u of the top limit, u of the top limit is u of 2 times 4 plus 1, which is 9, and u of the bottom limit, which is 2 times 0 plus 1, which is 1. So this is this, because this is this. So we get this to work, we get away with it again, because all we're doing is unwrapping the chain rule. Huh? Okay, so this is exactly using this. Huh? But because of this notational convenience of unwrapping the chain rule, the way that this thing fell out for us when we did our Usub was like this, and we had it like this. It was like this over this, which is exactly the same thing. And again, the point of this is not a proof. This is not a proof. I'm showing you that this weird thing of breaking up the u and the new extra wrinkle of reassigning the labels on the top and the bottom in terms of u instead of in terms of x using the Usub, I'm showing you that it is working because of unwrapping the chain rule. Yeah? So it is going to give us the right answer. We can evaluate this, and we don't have much space, I'm gonna erase a bit of the board just to get the answer. So we'll continue from this line right here, and then this thing becomes what? Let's pull out the half, and then we're going to have 9, 1, and we have the antiderivative of square root of u. It is 2 over 3 u to the 3 over 2, and then this simplifies. This is 1 over 3, pull out this constant, and then we're going to have 9 to the 3 over 2 minus this. So square root of 9 is just 3, right? So 9 to the 3 over 2 is going to be 3 to the power 3, which is going to be 27. So this whole thing is just 26 over 3. And we get the answer. Huh? And it's just it's a bit faster because we don't have to turn this thing back into the antiderivative in terms of x. Well, over here, sorry. We don't have to turn this guy back into the antiderivative in terms of x and then evaluate it in terms of the x limits. All we had to do was change the limits from here, which are in terms of x, to here, which are in terms of u, using the u-sub like this, which wasn't very hard, right? So we can carry out the whole thing from this point just in terms of u, get there faster. So it is worth doing this. It is a faster way to get the answer, and it's just another extra thing to learn about this U-sub procedure. Okay, so let's do one more example when I raise the board, and then we'll talk about symmetry. Okay, let's do this example. Integral from 1 to e of natural log of x over x dx. Okay, so solution. There's only two possible choices of u, right? We either let it be the log or the 1 over x. And if we try the log, then du by dx is 1 over x. And we quickly see it's the right choice, because then we have du equals dx over x. Yeah? Cool. So then we can rewrite this. Let's call it star. My advice is that you focus first on rewriting the integral and then do the limits. So if we rewrite the integral, so let's just do the integral without limits first of all, then we see that this log now is u, and this dx over x is du, so that's easy. Now let's think about the limits. So when we stick in x is equal to 1, log of 1 is 0, right? You need to be happy with what the graph of log looks like, right? Again, as I said many times, we've got to be very fluent and comfortable with these elementary functions, which we're going to use all the time. It'll save a lot of time the quicker you know what these guys look like. So log of 1 is 0, and log of e is 1, in case it's not clear. So log and e are inverses, so since log and e are inverses, we have log e to the x has to be equal to x, right? So in particular, log of e is equal to log of e to the 1, which is just equal to 1. So log of e is 1. Yeah? So that's how we get this top limit. So let's put this in a box. So then this thing, let's put it over here. Let's call this star star. So star star is equal to the integral from, oh, no, we've already done integral. Let's do the antiderivative. This is equal to this thing from 0 to 1 of u squared over 2, which is just 1 over 2. And that's it. So this is a very quick, very easy thing to do. Yeah? Yeah? And imagine the pain we would have trying to calculate this definite integral with a Riemann sum. So it shows us how far our technology has already got just a couple of lectures in. We can do these things. That would have been an incredible struggle pre-Newton and Leibniz in just one line. Yeah? Cool. All right. That is it for examples of definite integrals. It's really not that much different than doing indefinite integrals, just this replacement of the endpoints using the U-sub. Okay, cool. So we have a final thing to talk about, and that is symmetry. So let's underline this and talk about symmetry. So recall. We say that U is even if and only if U of x equals U of minus x. So as always, we're going to draw a picture. We're going to visualize this. What does it look like? This is x. This is minus x. If we sort of sketch something like this, then we have the mirror image on the opposite side of the y-axis. Yeah? And U is odd. So if and only if is often abbreviated as IFF. We have U of minus x equals minus U of x. Let's just re-emphasize that this is even. I think I want to change color. Let's do that again. And let's do an example of something which is odd. It's harder to draw. I'm struggling to draw it. Reflecting like this. Okay, I don't think I did the best job, but you see what I'm trying to do. Huh? So this is an odd function. That looks a bit better. Yeah? So the classic odd function is just f of x equals x. Yeah? So, a couple things to note. Oh, let me say that this is odd. Let's label it odd. You can also call odd antisymmetric. Okay, a couple things to note. Note, if we integrate an even function from minus b to b, then it's just equal to twice the integral from 0 to b of x if f is even. And it just follows on the picture, right? So if this is b, and this here is minus b, then what is it? Then it's this stuff plus this stuff. But the area here is the same as the area here, so the total integral from minus b to b is just twice the integral from 0 to b of this thing. Yeah? And now this b to minus b. If we consider if f is, let's call it something else, if g is odd, then what do we have? Integral from minus b to b, g of x dx. Take a look. So, for an odd function, this stuff is like, well, for this particular example, we have all this positive area here, we have this negative area here. And if we take the absolute value of the negative area, yeah, then the absolute value of the negative area will be the same as the positive area, because we can just see it, right? So we have this positive area added to this negative area, they will exactly cancel each other out. Yeah? So then this stuff will just be equal to 0. And that is very useful because sometimes you can be faced with things that look very hard like this. Yeah. And again, we know elementary functions. We know what the graph of tan looks like. This is minus pi over 2. This here is pi over 2. Yeah. I don't think it's a very good graph of tan, but basic features are right. And in particular, it's an odd function, right? In fact, if you, of course, know that tan of x is just sine of x over cosine of x. Sine is odd, cosine is even. The product of an odd and even function will remain odd. Just check for yourself. Huh? So what we have here is an odd function on the top and an even function on the bottom. Yeah? So that means this is indeed a product of an odd and even function. So overall, this is an odd function. So I'll just check. So tan, tan of minus x over 1 plus minus x squared plus minus x to the 4 equals minus tan of x over 1 plus x squared plus x to the 4. And yeah, it is definitely an odd function. So this thing, by what we've learned, by this principle, is just equal to 0. We don't have to work hard for this. If you notice it's an odd function. So again, this is another thing that could be thrown at you. You could have a bunch of functions given to you in a row that you apply U-substitution to, and then you can have something where U-sub is no use at all, right? So this won't. You can try as many U's as you want with this. It's not going to get you anywhere. But if you think about what this actually is, what this function looks like, and remember symmetry, you can quickly see that this has to be 0. So this is actually a good question to ask. This is really checking that you're thinking about what you're calculating instead of just following an algorithm without thinking about what it is first. Huh? Cool. All right, so that's it for today. Have a great weekend. I will see you all next week.